So just to recap everything that we've said, we've got everybody scheduled for taking their quizzes, and then I'm going to post your project tonight on Edmodo at 9 p.m. and it will be due on Friday, April the 1st in class. Our goal for today is and tomorrow is to talk about solids with constant cross-section. We're going to be trying to find the volumes of solids using integrals. And I've actually put the notes for today and for tomorrow on Edmodo, so if you have iPad or iPhone, go ahead and get that out. Pull up today's notes so you can follow along.
Is this one chapter 5?
No, 7. Chapter 6 is kind of a weird chapter, and I fragmented it and reorganized it into other chapters. So it's not that we skipped it entirely, it's that we did it in pieces.
Friday, April
1. So our goal is to find the volume of solids. Now the general problem of finding the volume of a solid is actually a hard problem. And so we're not going to solve the general problem. In the general problem, I might have some weirdo solid that looks like this, some three-dimensional figure, and then I would have to find the volume of this. We're not going to be capable of doing the general problem, but we're going to be capable of finding the volumes of a lot of different solids. And our goal for today is the specific problem of volume of solids with constant cross-sections. Now, let's build up to this. We want to start with solids that you probably learned about in geometry. If I take something like a regular pentagon and I extrude it so that it forms a solid like this. This is a little hard to visualize, but I'll do my best to make it visually appealing here. Then what I have is this really interesting solid with two congruent pentagons for the end caps, and then I have faces that are all parallelograms here. Do you see that? And in geometry we call that a prism. Do you remember that term from geometry? And the key thing about our prism is that the volume of that prism is simply the area of the base multiplied through by the perpendicular height, like that. And the idea is that we're taking this area here and we are multiplying it just like that, and so we get a volume that is area of the base times the height. Is that familiar to you guys, or at least does it make sense if it's not familiar to you? It's a solid, that's right. It's a solid shape. Let's see here. Let's see if I can show you a good prism. Aha! Here's a good prism. A book is a good example of something that is essentially a prism. We have a face, or an end right here that is a rectangle. We have a congruent rectangle on the other side, and we take and multiply that rectangle through the length of the book, so that the volume of this book is just the area of the rectangle, length times width, times the height, just like that. And all of you know length times width and height for a box. Okay? Let's see here. What other sorts of prisms and prism-like shapes could we make? We could have, for example, a cylinder that has two circles as ends, like so. Weird. It changed the size of that circle. Did it really?
The line.
There. Okay, the line didn't snap. Okay, and so if I wanted to find the volume of this cylinder, then I would say the volume is the area, which is pi r squared, times the height, h. And behold, the volume of a cylinder. Volume is equal to pi r squared times h, or area times height. And the idea here is that I'm multiplying the area of the circle through the height h. It's really that simple. Now on your notes there, I show you a particular solid that is not a prism, but it looks very similar to a prism. And so I'm going to try to draw that like it is in the notes. So imagine here that we've got an x-axis and a y-axis, and now I'm going to take and make a solid by well, this is my best attempt at drawing this whole thing. Now I'm going to try to draw some kind of a solid that is going to have its base in the x-axis. Boy, that just isn't drawn very well. Let me try that again. I got to get this guy. It's parallel. Three-dimensional drawing is tough for me. Is it tough for you?
Yes.
Okay.
I can't do it.
Let's try that. Is that better? Can we sort of see it?
A little bit.
So the idea is that we're going to have an equilateral triangle here. So we've got an equilateral triangle here that's going to sit on top of the y-axis. And then we have a smaller equilateral triangle that's going to be parallel to it like that. And then we have a solid that's formed by connecting these guys right here. And so the whole base of the solid is going to reside in the xy plane. This is the bottom of the solid right here.
Are there only two axes here?
Only two axes? Well, there's actually a third z-axis that points straight up like so. So our z-axis comes out like that. But we're not going to use the z-axis for computing it. And so, yeah.
So normally, because they're congruent, the two sides will be of the same, more or less. Well, obviously they're congruent, but they don't have to be the two of the same size, right?
Ah, very good. So here's what I want you to notice. The two ends right here are not congruent shapes, but they are similar shapes. They're both equilateral triangles. Okay? And now if I were to take a plane, let's see here. Give me a plane. There. If I were to take a plane, and let's make this dotted so we understand that it's a plane. And cut perpendicular to the x-axis. Now that's going to be tough. There we go. That's pretty good. If I were to take a cut that is perpendicular to the x-axis, so that we now get a shape like this in that plane, all of the shapes that I get when I cut perpendicular to the x-axis are going to be equilateral triangles. If you're having a hard time seeing this, it looks better on the notes that I provided for you on Edmodo, and I'm not seeing a lot of you with those notes out. So please get out an iPhone or iPad and take a look at those notes. Access denied request has expired. I have no idea.
Can you turn off the Edmodo and edit on the...
Oh. Yeah. Okay. So we call this solid a solid with constant cross-section because when I cut perpendicular to the x-axis, I get the same shape every time. Not the same size shape, but the same shape every time.
So why is the x-axis and is not just because of
Some trying to see it in 3 dimensions. That's exactly right. Yep, there we go. And you can see the solid right here in these notes to the best of my ability to draw it like that. Okay. Now, I want to actually illustrate this with a couple of real solids. Here's an example of a solid with a constant cross-section. And if I were to take this solid and first of all put it in the xy plane, and when I put it in the xy plane, then I would say that its base would look like this. So this is the base of my solid, and I can actually draw it here. Ooh. Try it again. Just by tracing along. It's having trouble because it's actually touching the board there. Go out to
What
here.
is that? You're moving out.
This is my daughter's violin shinra.
Oh.
Okay. All right. So we've got the base of the solid sitting right there, and now the cross sections happen when you take that solid and you cut perpendicular to the x-axis. When you do, you get this area. That's the cross section. And if you take a look at the cross sections that you get when you cut like that, all the cross sections for this are rectangles. The base is not a rectangle, but the cross sections are rectangles. You see the difference? So we can draw the base in the xy plane, and then separately, the cross sections are going to be formed, the shape that is formed when you make a plane perpendicular to the x-axis and cut through that solid, just like that. So if I were to try to draw the solid 3-dimensionally, it would look something like this. Here, like that. And it's hard to visualize, but I did okay. Alright? And you can picture that every time I cut perpendicular to the x-axis, like so, I'm going to end up with a shape that is a rectangle. And so for that reason, we call this a solid with constant cross-section, because all the cross-sections are the same shape, rectangles. Yes?
the cross-section change size?
Exactly so. Yes. Right, exactly. The base does not have to be, and in general will not be, a special shape of rectangle or any other kind of shape. That's exactly right. So we've got two things going on. We have the base, we have the cross section, and those two shapes are not the same.
So can you show the base of that object?
That's the base.
Oh, yeah.
This shape right here is the base.
And the cross-section we cut from this.
And the cross section would look like that.
Okay.
Yes, sir.
Does the cross section have to have the same ratio as
Because it's a similar shape, it will be proportional. It will have the same ratio. Yep. Yes, sir.
What is converging? You mentioned it in Wikipedia. You mentioned that eventually the two.
Oh, so converging is a concept that you're used to. It is the idea of a limit. So if I say the limit of h goes to 0, 2h over h equals 2, then we would say that the ratio of 2h over 2 converges to. Okay, where are we? Here's another example of a solid with a constant cross-section. Now here, I would not talk about a base so much as a central plane, right? But if I cut through that central plane, like so, then my base, if you will, is going to look like this, like that, and then the cross sections would be found by cutting perpendicular. And when I cut perpendicular and take a look at those cross sections, every single one has what shape? A circle. That's exactly right. So if we take the cross sections and cut it out just like that, what we get are these thin little circles that are all of different sizes. You see what I'm saying? Yes, great question. The way the problems are going to be presented to you is going to be, a solid has basic such and such, and the cross sections are blah, blah, blah. What is the volume of that solid? Yeah. So in general, I've taken these objects and decided on base and cross section according to how I could get cross sections with a constant shape. Here I can see I've got circles all the way down this way, so I'm going to cut it like this. Yes.
So do you pick what kind of cross sections you get? Like, if this is a cup, you can cut it that way.
Yes, that's right. I could cut it like this, but when I do, I get cross sections that are not the same shapes. Some of them are going to be thin rectangles, and others are going to be like sort of trapezoidal, and so on and so forth. So that would be a pain in the neck, and I'm not going to do that. Okay? So our goal now is to be able to find the volumes of these solids. And here is our plan. What we're going to do is we're going to cut our solids into lots of little cross sections, and each little cross section is going to be approximately a prism. And we can add up the volumes of all those prisms, and we get the volume of the solid. Does that make sense as a plan? Maybe? Kind of? Let's see how it works. Okay, let's take this solid right here as an example, and to make it realistic, I'm going to show you some of those cross sections that we've got going on here. Here's a cross section, there's one, and there's one. Okay? Everybody understand how I'm taking my cylinder, or my whatever it is, my cup, and I'm slicing it up into lots of little cross sections. Now, each cross section is going to have a certain width to it. So this is going to be a representative cross section that I slice. And the way that I find that representative cross section is that it has a width of dx, and this cross section is going to have a radius that is determined by my curve. And if I choose the largest possible radius in this subinterval, then I'm going to get a cross section that will actually have a little too much volume. And if I choose the smallest radius in that subinterval, I'll get a cross section that has a little bit too small of a volume, right? But either way, I can take this guy right here and pull him out of, abstract him out of the diagram to get a single cross section. There, that's what I got there. Single cross section that is going to have a width of dx, and it is going to have an area of A. Now, since my cross section is a circle, that area is going to be pi squared, right? Okay, let's just leave it at A for right now. And so, let me actually call this delta x, since it's not really infinitesimally useful. Okay? And here's my point. Since this guy right here has constant area A, the volume of this little piece is simply equal to area times delta x. And if I cover the entire solid with these little pieces that I've done right here, then the volume is going to be the sum of all of the volumes of these little prism pieces. So that the volume here is approximately the sum from I equals 1 to n of area times delta x. That's where we start. Now, the prisms that I've drawn are not exactly the same shape as the piece. If I really took a real knife and I cut my cup here, which I would not do because this came from paint, if I cut right here, like that and like that, then I would end up with a shape that is not a prism because the circle on this side is a little bit larger than the circle on this side. Okay? So what I'm doing is I'm only approximating. I'm choosing to pretend that my little thin circular slice has a constant radius, even though it doesn't. That's okay, because if I choose the largest radius, I will get an upper bound for my volume. If I choose the smallest radius, I get a lower bound for my volume. And if I let the number of slices go to infinity, guess what happens? The upper bound and the lower bound meet And that number that I get is the volume of this solid. So we'd say that then the volume is exactly equal to the limit as my number of slices goes to infinity of the sum from I equals 1 to n of a sub I over x sub I. But if you look at this, this is exactly a Riemann sum. And in particular, because I'm letting the number of subintervals go to infinity, this is the limit of a Riemann sum, which is a definite integral. So that the volume of a solid with constant cross sections is just going to be the integral of the area of the cross section times the width. And if you can picture this, then it turns out finding the volumes is pretty easy. So let's make sure we're reading this correctly, and then we'll actually come back and compute. Okay? So what this is saying then is that my volume is going to be the sum or the adding up of area times thickness at each point x along the curve. And if I do area times thickness for each point x, then I get the entire volume. In other words, it's generalizing our formula for the prism. For the prism, we simply took the area of the base and we multiplied it through the height. Now we're taking a variable area of the base and we are integrating that through the entire formula. Does that make sense? Okay. Let's see how it works. Peter.
Just want to make sure that so the A area is constantly changing.
Exactly. Very good. As I move from x equals 0 out to x equals, what does that look like? Maybe 10 centimeters? Something like that? 15?
A little bit more than that. Yeah,
15 centimeters? As I move from x equals 0 to x equals 15 centimeters, the area of each circle will be getting larger or smaller, right? But if I take each circle at its particular point and multiply by dx, I get the volume of that little segment. And if you now add all those up, ta-da, you get the total volume. Okay? Now let's do this in this way. The way these problems are usually posed is like this. A solid has, as its base, the trapezoid defined by y equals negative 1/3 x plus 3, the y-axis, the x-axis, and the line x equals 3. This is the base. Now we are also told the cross sections of the solid perpendicular to the x-axis are equilateral triangles. And now find the volume of that solid. Okay. There's our setup. Students will sometimes react to this problem by trying to visualize the solid. And you can try if you want to try to visualize that solid, but I find it very difficult to do so. If you want to visualize the solid, you're going to have to do it with some kind of perspective drawing where you have the y-axis and the x-axis like this, and then you try to draw equilateral triangles like so, and make your base trapezoidal like so, and there's your solid, and there it is. That's sort of hard to see, isn't it? That's going to help you. And it doesn't help us solve the problem. So instead of trying to visualize the whole solid, we are going to use two sketches to help us solve this problem. First of all, we're going to use a top view in which we see the base. We're going to sketch the base. And so here we go. This is our base sketch. And we're going to look at the x and the y axes directly from above. And when we do, we get to graph all of the base equations that were given to us. So we have the y-axis, we have the x-axis, we have the vertical line x equals 3, and we have the line here, the y equals negative 1/3 x plus 3. That's the sketch of our base. And what's going to happen is that the solid is going to grow up out of that base with cross sections that are, according to the problem, equilateral triangles. But you're not going to see the cross section here, except you're going to see the very bottom of it by creating for yourself a representative cut that is perpendicular to the x-axis. Like that. You see it? So all that this diagram shows us is the base and one representative cross-section, just the bottom of it,
And that's how big it is.
and that's how wide it is. That's exactly right. And what's going to happen is this cross-section right here somehow is going to be an equilateral triangle coming out of the board. Any questions about our first sketch? It's not giving us complete information. We are not seeing the whole solid right here. If we were to try to draw the whole solid, I could try, but it would look yucky. Yes?
I just wondering again how we got a dx.
Oh, yeah, that's easy. The dx is a little piece of x along the x-axis right here.
So that cross section is this way.
The cross-section is this way, perpendicular to the x-axis. Yep. I'm taking a mathematical knife and I am slicing perpendicular to the x-axis. Okay. The second sketch that we're going to have is a sketch of our representative cross-section. And for the cross-section, I'm going to pay attention only to the language about the cross-sections. The cross-sections are all equilateral triangles. So I'm going to draw for myself a little prism that has an equilateral triangle for its base, just like that. And this part down right here, at the very bottom, is this part that I cut right here. That's the connection between these two. So I sliced here, took this guy out, and turned him so that I could see him like this. So this portion right here is parallel to the y-axis, and this portion is in the z direction coming out of the board right there. So what I'm looking at now is a side view of just the one cross-section. Yes, sir?
Why is it not a trapezoid?
Why is the cross-section not a trapezoid?
Yeah.
Ah! Because the cross-sections of the solid perpendicular to the x-axis are equilateral triangles. That's the way the problem is specified.
Right.
So if I were to cut,
It's not a visual.
it is hard to visualize, and that's why I don't recommend trying to visualize the whole thing. I could try. Let me try for just a second, and if this messes you up, then just avert your eyes. But then I'm going to go erase it all, because you're going to see it's not going to help. So Earl, if I were to try to draw it, I would have to draw an equilateral triangle coming up out of the board there, and then connecting so that I get equilateral triangles all the way down. You see that? So it would be like a tent almost.
A tent.
I'm with you.
Oh, that's true.
But it would be a tent that would start wide at the back and go narrow as you go towards the front. Does that make sense?
So,
So we can do this one.
Yes, we're looking at a tent from above.
Wait, from above?
Uh-huh. We're seeing a tent from above
Oh,
with
Yeah,
the high point back
I
here
like this, and you can actually see it.
and the front point down there. As I said, hard to visualize, probably not worth it. So rather than try to visualize it, I draw just the base, which is easy, because it's defined by these curves, and I draw just the cross-section, which is also easy, because they tell me what shape to pick. Okay? Now, the only tricky part is, I need to provide some definition for this length right here. Keep in mind, this length is that length, the bottom right there, And this distance is a familiar calculation. Top curve minus bottom curve. It's the distance from here to here. And so that distance is negative 1/3 x plus 3 minus 0. So look at what this is saying. For each point x, I'm going to have a different equilateral triangle. And for each point x, the distance across here is going to be negative 1/3 x plus 3. So when x is 0, this distance will be 3. When x is equal to 3, this distance will be 2. Everybody see it? Okay. Now, we're almost done. The only trick is I need to know what the area of an equilateral triangle is. Ooh, geometry, geometry, geometry. File not found. Internet. Okay. Area for an equilateral triangle is side squared root 3 over 4. What's that? Well, okay, I can prove it to you. If I prove it, will you remember it?
Probably, yes.
All right then. Did you not prove this in geometry? Oh, a long time ago. Let's look at that. Okay, so here's my equilateral triangle, and I'm going to give it a side of S. And what is the measure of each angle? 60 degrees. Aha! So an equilateral triangle is really two 30, 60, 90 degree triangles back to back. Yes? So that if this is S, this little part is S over 2, and that little part is S over 2, and that's S, of course. And this is S root 3 over 2. And so now the area is going to be a half of the base, which is S, times the height, which is S root 3 over 2. That gives me S squared root 3 over 4. Ta-da! See? Easy peasy. So that means that because my side here is negative 1/3 x plus 3, the area of my representative piece, excuse me, that is an area, it's not a differential area. The area of my representative piece is going to be the side squared times root 3 over 4. And I can represent that as the area as a function of x. This is the big thing, the hard thing that I need to construct in order to be able to find this volume. Once I have area, I'm good. I'm just going to add up all the areas. Yes?
Actually, I don't understand the dx part, so is dx like the vertical part?
So dx is actually the width of my slice. I'm cutting through like this, and the width of that slice is dx, and the length of my slice is negative 1/3 x plus 3. Is that better? Once you have the area as a function of x, the game is won, because the volume is automatically the integral of area dx. Each one of these pieces is going to have a volume which is area times width. And if you now add up all the pieces from x equals 0 to x equals 3, then you get the whole volume of the entire thing. So it's just a matter now of substituting the area. And integrating. Any ideas for integration? That's not a bad thought. For a lot of these volume problems, you will have calculator available to you. And integrating by calculator is your first choice. Let's pretend that we don't. Now what?
Find out the constant multiple.
Good. Out comes that constant multiple. Well, now that you have, file that away in your bag of tricks.
Yeah.
Yep, good. Where from here? Substitution or its cousin? Repair, that's right. I think repair seems good, right? So, because if I let u be negative 1/3 x plus 3, then du is negative 1/3, and I've got all of that except for constant. So, negative 1/3 on the inside, so that I've got du sitting right there. Negative 3 on the outside to repair it. And that gives us negative 3 roots 3 over 4 times, now the integral of u squared, you integrate the form, and get 1/3 u cubed from 0 to 3, just like that. And this gives us times 1/3 times, let's see here, that's going to give us negative 1/3 times 3 plus 3 is going to be 2. 2 cubed is 8, minus 3 cubed is 27. And 3's canceled here. And 8 minus 27 is negative 19. So that I get 19 roots 3 over 4. I think in the notes I have 3 times that, which is a mistake. Do I have 57 root 3 over 4?
That sounds familiar from what you're putting.
In the notes.
Yes,
Yeah, so I just failed to divide by 3 in that there, so I'll need to fix those notes. Okay, now the first time we see this we go, this is kind of weird. So let's immediately do a second one so we can see how this works out. Review the process. We need a sketch of our base and a sketch of the cross section. We need an area formula for the cross section, and then we simply add up area dx to get the entire volume. So that's actually not so bad. The trick is to find the area. So let's take a look at a second one. Solid as a base, y equals x squared, and y equals 4. The cross sections perpendicular to the x-axis are squares. Find the volume of the solid. So, immediately draw the base. Go. When you draw the base, don't forget to label intersection points. I forgot to label intersection points. your base should be this parabolic slice right here with the intersection points of 2, 4, and negative 2, 4. Just like that. Good. Label this as your base so that you can keep your head straight on this. Now, the hard part can be the easy part. The hard part for students can be easy if you remember one thing. The base does not look like, almost never looks like, the cross-section. Students will take this base right here and they'll try to turn the cross-sections into something like that. Instead, the shape of the cross-section is what the problem says it is. The cross-sections are squares. That's exactly right. So to get that cross-section, I'm first of all going to cut perpendicular to the x-axis, and that cut looks just like this, perpendicular to the x-axis. And that cut will have a width of dx because it is a width along the x-axis right there. And now I'm going to take that cut, I'm going to come over here and I'm going to draw myself a little prism with a shape that is a square, and the bottom of that prism is going to be the bottom of my cross section. And that's how these two are connected. Earl, if you're trying to visualize it, then what you would have to do is to visualize something that had basically, well, it would go sort of up like that. So that when you cut into it, you get this way, you get squares every time. That's really hard to picture. So,
Teachers, pardon the interruption for an announcement. Lacrosse team will be practicing at Cedar Lane today. Baseball will be practicing at Big Show. Softball will be in the gym. The boys basketball open gym has been canceled for today, as well as team pictures. They are postponed. And one last announcement, Mr. Kennedy will have the March Madness brackets at lunch today. So if you're interested in participating, pick a bracket up. They're due back into the office by Wednesday. Thank you.
okay. So now, the only thing I need to know here is the length so that I can get to the area. That length is top curve minus bottom curve. And so that length is 4 minus x squared. So I can immediately write the area in terms of that length by knowing the shape. And the shape is a square. So the area is side squared, which is going to be 4 minus x squared, y squared, just like that. Once I have the area, the game is won. I'm going to be integrating. My volume is going to be the integral from. Where is my first x value? Yes, that's why I labeled those intersection points. And my last x value? Positive 2 of area dx, which is the integral from negative 2 to 2 of 4 minus x squared dx. Does anybody notice anything interesting about the limits of integration?
Double opposite 2 times 0.
Yep, that's right. So we can double and go from 0 to 2 because I've got an even function. And now, what's my strategy for evaluating this integral? Substitution, u equals 4 minus x squared, du equals negative 2x dx. I'm missing a big x right there. That's going to be the problem. Repair, same issue. If I can't substitute, I can't repair. What's that? Calculator, could you, right? Do that?
Just do the little supplemental calculus.
Well, I've got to, right, but I need an antiderivative here. Algebra first, right, exactly. There we go. Multiply this guy out, I get 16 minus 8x squared plus x to the 4th. And now we've got an easy integration. From 0 to 2. This is a little bit of a pain. I get 32 minus 8 times 8 is 64 thirds plus 32 fifths. And that's a good enough number, and we can leave it right there.
Oh,
Tonight, I'm going to give you some problems. There will be directions, but this is key. On every single one, you're going to draw the base, you're going to draw the cross-section, you're going to give you the area. Do not think that you're going to go home and not practice. You need to practice.